So today we will dive into the basics of deep learning. What is deep learning? Why is there so much hype about deep learning? What is the history of deep learning? How did it evolve? And why are companies spending so much money on deep learning? But let me tell you first how deep learning is related to all the other different fields of learning. So here is a Venn diagram. As you can see, this is deep learning, which is a subset of machine learning, which itself is a part of the much greater artificial intelligence. So we have artificial intelligence, whose subdomain is machine learning, and the subdomain of machine learning is deep learning. So what exactly is deep learning? Well, deep learning has algorithms that are inspired by the structure and the functions of the brain. So, in the next few chapters and lessons, whatever you will learn, you will know that all the structures have somehow vaguely, loosely, or a lot inspired by the structure and the functions of the brain. Okay. So, now before I go and explain more about deep learning, I think we should all take some time to know about the history of deep learning, how it started, where it started, how it has evolved. Now, I know this is not a very important part, but it gives a very great appreciation for how we have overcome all the problems and where we are right now. So, now, even though deep learning is very hyped right now in the market and it is a very new learning field, but the idea of deep learning started way before. It all started back in 1958 when we had the first idea of perceptron. So, perceptron is inspired by the biological neuron. You might have remembered this from your bio classes. If not, let me tell you. Neuron is the basic building block of the brain. I know most of you don't remember neurons and biological neurons. So, before I go and explain about perceptrons, let us look into neurons. So, this is a biological neuron. All these here, these are known as dendrites. In these dendrites, we have electric pulses that come in and some computation happens here in the nucleus of the cell or the cell body, and then all of this is then passed through the terminals to other different neurons. So, in short, you have one neuron here. It gets all these electric pulses here. You have some computation here and it gives all the outputs. These outputs may sometimes act as input to other neurons. Get the idea? Okay, so this is the structure of a biological neuron. Let us see how this can be implemented mathematically for an artificial neuron. So these are inputs x1, x2, x3. By the way, you can have as many inputs as you want. So here you can have xn inputs. For this example, let us just have 3 inputs. So these inputs are passed into this cell body right here and something happens in here and we get the outputs. Okay, so now let us see what actually happens. So we have inputs. These inputs have been given weights W1, W2, W3. Now it is important to give weights because sometimes some input might be more important than other input. Suppose we have a sentence, there is a dog. In this sentence, the word dog should be given more weightage than there is or a. That is very simple and known for us. So that is why we have inputs and we have to give them weights depending upon how important that input is. So that gives us this. So the first thing that happens inside is we have a summation function. So the first step is a summation function. So you have x net, which is multiplication of w1 with x1 plus w2 x2 plus w3 x3. This gives us what? X net. So this is our first step, summation. Our second step is passing that summation value, that is x net, through a function. So second step is passing the function x net through a function. Now this function is known as an activation function. This is the same as activation in neuron, which tells which part of the brain that should be activated. So that is why the name activation function. Now there are a lot of activation functions and I will go into the details later on in the chapter. But for now, let us just keep it as an activation function. So we have the summation, which is followed by an activation function. This activation function gives us the output. So once the summation is passed through the activation function, we get the output. In this case, y. So that is the structure of a perceptron. Now, this was discovered in 1958, as I said. So why did it take so much time? And why is it that deep learning is right now in the hype? That means, what happened? What were the problems with a perceptron? Let us look into that. Problems. Well, the first problem was, it was a single neuron or a single perceptron. By the way, perceptron is also known as a node. So, if you will look into the brain structures, you will realize that a brain has more than just a single unit. It has a lot of neurons, layers of neurons, all those neurons are interconnected. So, it's like a dense network of neurons. So, a single neuron was not enough for us to do any kind of experiments. The second problem that we had was no learning. That means, if you will look here, we have these inputs that go in the weights and we get the outputs, right, after some computation. But the problem is, there is no learning. In any learning intelligent program, there should be some learning. The model, the system has to understand what it is doing, what it is saying. So, that means here we just had a forward movement. Whatever be the input, the output, the loss, the mistake is always going to be the same. So that means it had no learning. That brings us to our next part. The next big invention, MLP, multi-layer perceptron. So, we know the problems with perceptron. One of the biggest problem was it was just a single node. So, scientists came together and in the 1980s, they built layers of perceptrons. But before I dive more into it, let me give you an idea about the terminology. So, this is an input layer. Here is where all the inputs pass. This is an output layer. This is where you get all your outputs. So, here if you will see inside, this is known as a hidden layer. That means all the layers that is between the input layer and the output layer are known as hidden layers. Why hidden exactly? Is because these layers are neither directly connected to the input or are they directly connected to the output. They are somewhere in between and they result in giving the output and take in the input, but none of that is direct. So, these circle things, they are the perceptron or the nodes that we studied right here. So, here you have these inputs. This goes inside. You have the summation function first. That gives you x net. which is passed through this F function, which is known as the activation function. Okay, so you have the inputs, you have the hidden layer, you have the output layer. Now, there is one thing, all these are known as nodes like I said. So, the input layer has 1, 2, 3 nodes. Hidden layer has 4 nodes. Output layer has 2 nodes. You can have as many nodes as you want. There is no particular criteria. For this example, it has 3, 4 and 2 nodes. So, as the name suggests, multi-layer perceptron means more than one layer of perceptron. And how do they create these layers? By stacking perceptrons one above the other or one below the other in a particular row to form layers, and we get multi-layer perceptrons. Now again, this is a very old concept. So what were the problems with multi-layer perceptron? Well, the first problem was theory. It could only be proved in theory. There was no way how you could practically prove this thing, because now the reasons for this was, number 1, lack of resources. That means less computational powers. Our RAMs, the RAMs at that time and the GPUs, I don't think so they had GPUs, but the lack of RAMs at that time, that means low computational powers. So our computers were not strong enough at that time to actually compute this and prove this in practical. So it was left in theory. The other problem was lack of data. If you will look back in the 1980s, most outputs were just, or most data was just in the papers. There was nothing in digital format. So that is why, due to the lack of data and low computational powers, there was no way why this could be proved. However, surprising is this structure was back in the 1980s and we still somehow use a form of this structure. So now the next big time thing came in 2012, which is known as the modern era also. Modern era of AI. So what happened in 2012 is we now had high computational power, high computational computers, and we had data at that time. If you remember, in 2012 we had big companies like Microsoft, Facebook, Google, and they had tons and tons of data. So now how exactly did deep learning start? Back in 2012, Stanford had this competition called ImageNet. Now they had it every year, and since deep learning was not very popular, people used to stick with machine learning algos, classic machine learning like random forests or SVMs. But in 2012, a team used a basic deep learning algorithm to solve this ImageNet problem. So what exactly was ImageNet? Well, in ImageNet, the main task was to identify objects from images. Now remember, this was a very difficult task back in 2012. So they used a basic deep learning algorithm to actually solve this problem. And what was surprising was this algorithm beat all the classic machine learning algorithms by a very large margin, like very large. So in that time back, what happened is companies like Microsoft, Facebook, Google all started to pay attention on deep learning now because they could see the power of deep learning. Okay, so that was the history and it has still been going on. Now we have high resources, lots of data, and because of globalization, we keep getting new algorithms to solve new problems. Okay, so just to recap, even though we had all these ideas back in 1950s and 1980s, we could not actually implement them. If you will see the most classic methods that are being used right now in computer vision, you will learn about CNNs. These were also developed way back in 80s, 90s. But there was no way how this could be proved. But now that we have everything, we can prove everything, we can solve everything, and we can tackle more new problems. So, in the next classes, what I am planning to teach is about multi-layer perceptrons, deep into it. So, I'll teach about activation functions, I'll teach about calculating loss, I'll teach how they learnt everything, how the models have learned. Yeah, and then one by one, we'll go more into details and learn stuff about optimizers, back propagation, and other stuff.